So one of the questions that I get most frequently from investors, once they feel like they understand a little bit about cell programming and what that's going to do for the world is, okay, but what is it that Ginkgo actually does in the Foundry? What is the work that you do? And we figured the best way to help explain that was to just show you directly, to walk you through the Foundry. We'd obviously love to have you in Boston in person to walk through, but in the meantime, I'm going to ask Barry to take you through a video tour of the Foundry and introduce you to some of our leaders across software and automation who help make what we do in the Foundry possible. He's also going to introduce you to Patrick Boyle, who's our head of Codebase, which incorporates all of the biological data and parts and strains that we use in conjunction with our Foundry to enable projects for our customers across the entire cell programming landscape. Barry, take it away.
So you've already heard a lot today about the Foundry, but you may well be wondering, what do we mean when we talk about our Foundry? Well, first of all, the Foundry is one of the key pillars of our platform that we've been building at Ginkgo over the last 13 years. And I'm really excited to be able to show you some more of the detail about that today. Ordinarily, I'd love to be bringing you on a physical tour of our foundries and showing off the people, the technologies, the instruments, the robots that we've been developing over the past number of years. But today, I hope to still be able to bring you inside the foundry as best as we can and expose you to all of those incredible technologies. You're also going to get to hear from some of my wonderful colleagues. You're going to hear from Kristen Tran, who is our head of automation. You're going to hear from Jamie Cho, who is our head of software. And you're also going to hear from Dave Treff, who is our head of Devops and IT. And you're going to hear about how all those different disciplines and technologies come together to power the Ginkgo Foundry. One of the first questions that we always get from folks is, what is our Foundry and what do we do in there? And that's a very reasonable question because foundries and this concept of programming biology is foreign to almost everybody who hasn't been doing it for 20 years, like the team at Ginkgo. So I'm going to start there and let's talk a little bit about, well, what actually happens in our foundry and what is the overall process of programming biology. For us, it typically starts with an interaction with a potential partner or customer where we jointly develop the concept of a cell program that will help that customer make a new product or a better version of an existing product. Through those conversations, we'll develop a specification for the cell program that we're going to build with them. Once we've reached that agreed upon specification, the work is turned over to our cell designers who will refine and develop the concept and the specification of how we're going to make that cell program. And they'll continue to develop that using codebase from our collection, as well as nature's codebase, the cells and genetic assets that are out in nature. And our designers will bring those different pieces of codebase together to develop a detailed design. We put all of our best learning accumulated over many cell programs into those early designs. Once we have those detailed designs that are specified at the level of DNA sequences, all in a computational manner, those designs are handed over to our DNA synthesis and our build teams. And their task is to take those conceptual and computational designs and turn them into reality in the lab. So that starts typically with DNA synthesis, where we print out the new DNA sequences that our cell designers have come up with. Once we have those new DNA sequences, our build teams will take those DNA sequences and put them into the genomes of cells that we want to work with. We will finally, at this stage of the process, use sequencing technology, DNA reading, in order to make sure that we've made all of the right modifications to the DNA inside the cells that we're working with. Now we have a real life cell in the lab that is the physical instantiation of our designer's concept. And now the next question is, how does that cell perform? To answer that question, we hand those newly programmed cells over to our test teams who bring together a wide array of different capabilities that we use in order to understand how those new cell prototypes that we've been building perform. Do they meet the customer's specifications? Do they nearly meet the customer's specifications? Do we still have a lot of work to do? So those test teams use technologies like mass spectrometry, liquid chromatography, high throughput screening, next generation sequencing in order to understand what's happening inside the cells that we've built and to measure the performance of those cells. Typically, we will find that some of those prototype cells perform really well, and some perform so-so, and some don't perform well at all. All of that information across many different designs, we'll integrate together and use it to come up with a new round of designs. And then we will iterate through that process of designing, building cells, testing how they perform until we meet the customer's specifications. And a lot of the technology in our Foundry is oriented towards making that process as efficient as possible and investing in the tools and technologies that allow that process to happen faster and with a higher probability of success than has been possible previously. So when you see inside our foundries and when we're able to bring you physically to our site at Ginkgo, what you're going to see is, first off, what looks like kind of like a lab, but also a little bit different from a normal lab. And that's because for our foundry to be efficient, what we've had to do is start with a conventional lab and then bring a lot of concepts in from manufacturing, from operations research, in order to build scalable, high throughput, automated processes that allow us to more quickly and effectively program cells for our partners. And so what you will see in our foundry is not the typical row after row of benches with a scientist working at each bench. You will see some of that in our foundries, but what you will see more and more of is sophisticated instrumentation, robotics, liquid handling instruments, and a wide array of sophisticated and complex machinery and instrumentation that we use to amplify and multiply what our scientists are able to do in our foundry. We bring the best in robotic and software automation together with the unique skills and insights that humans have in order to be able to program cells more effectively with a higher probability of success than would ordinarily be possible. And so what you'll hear in the labs, what you'll hear in our foundries, is you'll hear relatively loud hum of equipment, of robotic arms, of instruments moving liquids back and forth. You'll hear that hum of activity that is largely consisting of robots and instruments scaling up and powering the work of our foundries. It's essential to our foundry that we be able to run many designs or prototypes through every step of that process in order to minimize the overall timeline of a project or a cell program to develop a cell that meets the customer's specification. So not only do we want to be able to look at thousands or tens of thousands of prototypes for every cell program, we also want to be able to work on many cell programs at the same time. Today, we work on tens of cell programs in the Ginkgo Foundry at any point in time. In the future, we want to be able to work on hundreds of cell programs at any given time. So when you put all of that together, you find you have a complex, multi-step process of designing, building, and testing cells. You want to be able to do that process at scale with tens of thousands of prototypes within each program. And we want to be able to do many programs at the same time. The result of that is that scale, logistics, operations, the throughput of our foundries becomes really important. Those robotic and software automation paired with what humans can do means that overall our foundry can do way more work and way more cell programs than would be possible by people alone. And so this really leads in nicely for you to hear from Kristen Tran, our head of automation, who will tell you about all of the incredible robotic automation that we use throughout the Ginkgo foundries.
At Ginkgo, we try to automate as much as we can. We start with small-scale automation, really accessible stations for scientists and engineers to walk up to, really easy for them to start using. Once we actually start scaling up, we can actually start stringing these operations together seamlessly on an integrated work cell, which really allows us to kind of really take off on that scale. It really allows the scientists' output to increase 10x, 100x, 1000x. And really, that's our goal. We want to maximize that. We want to automate as much as we can. And really, whatever they're going to let us do, we'll try it. Instead of having a scientist go from station to station, we have this centralized robotic arm that's going to handle all of the samples. And it's also going to record everything. And it's going to produce that valuable data that we need for our cell programs and for our code base. What my team and I do as automation engineers, we like to look at what the physical activities people are doing in the lab. We're engineering cells, and that requires a lot of precise handling of samples. What my team does is we take these activities in the lab that scientists are manually doing, such as pipetting, and we actually make a custom integration. So we integrate these in a work cell. With that custom integration, not only can we really control the timing and the precision of the activities, but we can actually track everything within our software so that all of the data can be collected and all of that can be reused for future engineering projects. For automation, in addition to automating manual processes that a scientist would normally do with the bench, we can actually go beyond human capability and miniaturize certain reagents and certain reactions. So an example of this is with our acoustic liquid handler that can actually dispense nanoliter droplets of liquid. With one of our core processes, we were actually able to miniaturize the reaction 50x. In addition to that, it increases the speed and the output. So our scientists are able to produce hundreds to 1,000x more output that they can trust and that they're able to go back to and reflect and really iterate on their process and on their design. I think there is a misconception that, we're trying to replace, the activities that certain people do in the lab. But the way that we look at it is we really want to augment the ability of a scientist. We want to increase their ability to perform experiments in the lab. We want to give them the peace of mind that it's going to be done faithfully, that it's going to be done with high precision and high quality. And with these different scales of automation, they can actually increase their output and create more valuable data for them to iterate on their process. Something that's really special about Bioworks 5 is, in addition to the large scale that it provides, there's actually all of this really interesting new technology where we're able to sense the success of each operation. So you can tell whether or not an operation failed, was successful, and record it. We use different types of sensing technology, including acoustics, light scattering sensing, light proximity sensors, and pinhole cameras. And what's really great is, we implemented this in Bioworks 5 in our latest facility, but we can actually take that technology and apply it to all the different scales of work that we do throughout the Foundry. So all of this technology that we're developing in Bioworks 5, we always have an eye on where else can we leverage this? What else can we automate? Where else is this going to be valuable for us? Really, that's how we develop our automation. We are always thinking about it in what are these new tools and how can they be even more helpful to Ginkgo and to our scientists. A lot of resources went into building Bioworks 5, but something that's really unique about the automation at Ginkgo is that we have our own custom integration and software integration. So we work really closely with our colleagues in digital technologies. We have a great relationship, and what we do is we try to think how can we leverage all of that technology that's already out there and make it really useful for Ginkgo and leverage it in a flexible way to apply to multiple programs. Our infrastructure through custom automation and custom software can actually be applied throughout the Foundry. It can be applied for different cell programs. It can be applied for different organisms. And it's kind of amazing the diversity of scientific processes that can be performed on the same set of infrastructure. I think we're only really able to do that because we have this in-house development team, both on the automation side and on the software side, as well as the DevOps side. We all work together really collaboratively to make sure that that integration is as seamless as possible. And we're constantly thinking about how can we scale? How can we be more efficient? We always have to pair that with flexibility, which is always quite the challenge, but it's a really fun challenge. All of our engineers at Ginkgo are really interested in being the ones that solve that problem. And it's been pretty amazing to see what the teams are capable of. We get to work really collaboratively with our engineering partners to create new technology, to create new capabilities on existing robotics. And in addition to that, sometimes we even have custom partnerships where we're able to create something truly unique for Ginkgo. Bioworks 5 is a really prime example of this, where we leverage existing high throughput manufacturing technology, but we're able to apply it to the synthetic biology space.
The process of designing DNA, which must seem like a very abstract concept, really involves using computers to go from ideas down to detailed DNA sequences that can be thousands or tens of thousands of letters of DNA long. Because those DNA sequences are very long, and because we'd like to be able to design many of them at the same time, we've built a suite of design tools, computational design tools, that our designers can use in order to come up with the best possible DNA designs for every cell program they're working on. When you see our designers working, what they're really doing is interacting with software tools, many of which are proprietary, that allow them to stitch different pieces of DNA together computationally in a quick and efficient way, almost as easily as you can drag and drop objects in a software package. But those objects are actually DNA sequences that we are subsequently going to print out. So once we've done that computational design process, which really looks almost like an architect or an engineer interacting with computer-aided design, then we move over into the lab. DNA printing. Again, that's a very abstract concept. Well, does it look like a desktop printer that you might have at home? Or what does it look like? Well, it's a lab operation, but it uses increasingly advanced, sophisticated technology in order to make the operation of printing DNA as cost-effective and reliable as possible. So we work with partners such as Twist Bioscience to use their proprietary technology for printing out, literally using inkjet printer technology to place individual DNA bases together in the right sequence so that we get the new DNA sequence that corresponds to what our designers have developed in our computer-aided design tools. So DNA printing really looks like a very, very complicated printer. Thereafter, once we have short printed DNA sequences of, say, 100 bases long, we next need to stitch those 100 base sequences together into 1,000 or 10,000 base sequence of DNA that encodes a gene for a protein or a set of genes for a metabolic pathway. And that operation, stitching those short pieces of DNA together, is again a lab operation. And it looks like a lot of liquid handling. It looks like a lot of moving small volumes of liquid from one source to a destination and mixing lots of different liquids together. And so that's a process where we rely very heavily on liquid handling automation to scale the amount of DNA molecules that we can build at the same time for many cell programs. Once we put that DNA into the cells, and that process, again, really just looks like a liquid handling process. We take a little tube of cells, we take a little tube of DNA, we mix some of the DNA into the cells, we treat them with some heat and some chemicals, and that helps the cells take up the DNA inside them and integrate the new DNA into the genome of the cells. Once we have that operation done, we then grow the cells. So we start with a tiny tube with just a handful of cells in it that have the new DNA. And we allow those cells to grow so that we have millions or billions of copies of that newly programmed cell. Those cells grow in either small bioreactors that look like miniaturized versions of fermentation systems at a brewery, or it happens in plates that have hundreds of individual wells in them so that we can grow many different populations of cells or many different prototype cells at the same time. Once we have those cells grown up, we have lots and lots of cells, then the next step is often to sequence them. So DNA reading. That's the process by which we read all the DNA that's in the cell and make sure that we've put the right DNA into the cell. That's an operation that happens on very sophisticated instruments, and the machine streams data to our proprietary databases and our data lake here at Ginkgo. And that data contains all the DNA sequences that are found in those cells. That's again a computational or a digital process. Once we know that those DNA sequences are right, then we move on to measuring the performance of those cells. And what that looks like is taking the cells, observing them via instrumentation that can say, look at the levels of particular molecules or identify the particular molecules that are being made by those cells, and really allow us to look inside the metabolism of the cell or the behavior of the cell so that we can understand how its performance matches up to what we expect. So when you see our testing operations in our Foundry, what you'll generally see are collections of instruments that are 24/7, taking small samples from a culture of cells and chemically analyzing those samples to understand what's in there so that we can understand how those cells are performing. You'll see in the Ginkgo Foundries, there is an enormous amount of work happening across many different cell programs at the same time. All of those physical operations, all that work that's happening is very hard to track unless you have really good software tools to manage the operations of the Foundry, and also to collect all of the data and metadata that is being produced across all of those operations, and bring all of that data into a location like a database and into a format that our scientists can analyze what's happening and decide what to do next. We've invested an enormous amount of energy and time over the last 12 years building proprietary software tools that are completely critical to the operation of our Foundry so that we can operate at a scale that would be hard to operate at otherwise, and at a level of quality and sophistication that would be impossible without dedicated software tools that were built specifically for our operation. And who better to tell you about that than our head of software, Jamie Cho.
The software we build is uniquely tailored to Ginkgo's Foundry's needs. Our software team has a lot of the same traditional skills that you see on other software teams. They know how to program in Python and Ruby, Rails, and React, and all of those skills. But what's really special about our team is we are all passionate about biology. And in fact, our mission is to make delightful software that makes biology easier to engineer. Ginkgo's unique focus on engineering biology at scale means that we have to build a software platform that can handle that level of scale. We have powerful workflow systems that allow us to generate and execute really complex laboratory workflows for actually manipulating that DNA and transforming it into organisms. This is a seamless process that the software enables. And likewise, we have built the platform so that it can actually pull data automatically from instruments and analyze that data, feeding it back to the beginning of the design, build, test, ferment cycle. So our laboratory workflow software actually keeps track of everything that's happening inside the lab. And a lot of these workflows are automated such that when instruments are processing the data and actually return the data, we're able to analyze it automatically and refer it back to the originating samples that generated that data. And this all happens seamlessly. Integration of all of those different components is really important when you're dealing with data sets as massive as the data sets that we're generating every day. This degree of integration really enables us to keep track of what's going on and then feed that information back into the current design, build, test, ferment loop But what's even more exciting is because we can keep track of all of this stuff, we can also apply it to future programs and get a head start on those. And this is what we call code base.
Not only have we had to build a huge amount of infrastructure in our labs, in our foundries, with equipment and people and processes, the same applies to data. We're generating a huge, massive amount of data across our operations every day. That data is being managed by our software, our proprietary software, but it's really all built on a layer of digital infrastructure that was built specifically for our Foundry. And you're going to hear today from Dave Treff, who's our head of DevOps and IT, about that digital data infrastructure that we've been building.
Usually companies that are big build big but inflexible, slow to change infrastructure. Small companies will build smaller and flexible, much more flexible, much more changeable infrastructure. At Ginkgo, we build big and fast and very changeable. I have to change stuff constantly. One of the things that we do is everything that we buy, for example, let's say we're buying some network equipment, we look at each piece of network equipment that's in the whole network or any computers that are in the Foundry or anywhere, and we look at it and go, okay, we're going to buy this today. Can we make it go faster next year? Or can we upgrade it so that it has more capacity for more data? Because of it's Knight's Law, right? If I was asked to do a 3-year plan, for example, we do 4x every year. So it's 4x this year, it's 16x next year, it's 64x year after that. So I have to have 64 times, or I have to plan for anyway, 64 times the amount of network, the amount of compute, and the amount of storage that's available. I've never worked anywhere like that. This is not normal. Well, it's really fun. I will tell you that. This is the most fun job I've ever had in my life. And you look at me, I've had a few jobs. What we do is we just stay ahead of the scientists. We buy bigger pipes, we buy bigger equipment. All of our software we make, and we have to make it because it doesn't exist. And the way we design our networks is obviously for things like, resilience, and I mentioned upgradability and flexibility and blah, blah, blah. But we also have, there's probably, I don't know, maybe a dozen different types of data that come out of these machines. We have to handle all of them, and we have to get it to the software that we write, which is all bespoke. And then we have to shuttle that around, and we have got to store it, and we've got to make it so that Patrick and his folks can find it, because that's the code base. We have built a custom network with lots and lots of security controls in them that go all the way down to the bit level. So there's security on the wire, there's security on the software, there's security in all the network switches. But one of the other things about that is that's really hard to do. You can't just do that, right? You can go out and buy it, but do you trust it? No, you really want to do it yourself. So what we did is we hired a couple of ex-military, 3-letter agency people who have a lot of stories they can't tell us. And they have been designing and helping us build our network and all of our processes to be secure. And what that does is obviously gives us a lot of peace of mind. Other companies outsource all that stuff. We want to keep it in-house.
So the output of our Foundry is a new cell, a programmed cell that does what our partner and our customer needs it to do. But that may not be all that they need. So sometimes our final product is the programmed cell, and we're able to hand that off to our partner for commercialization and production. Sometimes that cell needs to operate in a manufacturing process that we can help develop, perhaps in conjunction with our partner, or perhaps we do the work to develop that manufacturing process. Sometimes what our customer or our partner really needs is just a final product. They need a compound, they need a molecule, they need a protein that they can use for perhaps their application testing or to go directly into sales channels. In those cases, Ginkgo's product is the cell, the process, and whatever that cell is intended to make. We can help the partners close the gap from the newly programmed cell that we've developed for them to their final product. We have those capabilities across our Foundry and across our locations. So a core premise of our Foundry is that most cell programming projects follow a conceptually similar workflow. We've already talked about it, designing cells, building them, and testing their performance, and iterating through that loop. That insight means that we can build a general purpose Foundry that runs that general workflow for many cell programs at the same time. Why is that helpful? Well, it's helpful for one very important reason, because by running many cell programs at the same time, we unlock economies of scale. We're able to make sure that our foundries are at a higher level of utilization. Each individual piece of equipment is at a higher level of utilization so that we can make better use of fixed costs or capital investments and amortize those expenses across many cell programs and many operations. By working on many cell programs at the same time, we're also increasing our learning about how to do this process better. We're increasing the number of code-based assets that we have available to us that we can then use to make subsequent cell programs easier, as you'll hear later from Patrick Boyle. By working on many cell programs at the same time, we are able to reduce the individual costs of any given cell program. By doing so, we can increase the probability of success of those programs. We can reduce the costs of those programs, and that's value that we can offer to our partners. So by working on many cell programs at the same time in our foundries, we unlock economies of scale, which makes the overall process better. By doing so, we then get to work on more cell programs at the same time. And there's a virtuous cycle there where more cell programs translates into greater economies of scale and better value for our partners. So you can really think of the Ginkgo Foundry as being a combination somewhere in between a lab and a factory. And that's why we don't call them labs, we call them foundries, because we wanted to differentiate them from a conventional lab. But why foundry? Well, we're using the term foundry that was popularized in the semiconductor industry, where a foundry is really a chip fabrication facility that relies on very sophisticated equipment, very complex processes in order to be able to make an incredible product, a semiconductor chip. We thought that was a great inspiration for what a cell programming lab of the future could look like with investment. So that's why we call them foundries. One other reason why we like to make draw the connection to the semiconductor industry is because we've been greatly inspired by Moore's Law, the observation that over more than 30 years of development in the semiconductor industry, the complexity or the sophistication of semiconductor chips doubled roughly 18 months. And it did so by virtue of investments in the foundational tools and technologies of making semiconductor chips. Our belief, the premise of Ginkgo, is that with investment in tools and technologies, we can see a similar compounding improvement in the technology and in the what we are able to deliver to our partners, as was observed with Moore's Law in the semiconductor industry. You may think that that's speculation. Well, we believe that we are seeing that trend happen. We can empirically track the operations of our foundry. We can track how much work we're doing. We can track how much it costs us to do that work. And we can observe trends in how that amount of work and that cost of work is changing over time. What we're incredibly excited about is that over the course of the last 5 or 6 years, we've been able to see an exponential improvement in the amount of work that we do and an exponential reduction in the cost of that work on a per unit basis. That concept of exponentially increasing output from our foundry and exponentially decreasing cost to do the work, we call Knight's Law. It's a nod to Moore's Law that you've heard about. It's also a nod to my co-founder, Tom. Knight's Law at Ginkgo is really the result of an enormous number of people's hard work over many years. And if we want to give recognition to one person who helped inspire so much of that work, we couldn't come up with anyone more perfect than Tom. So the reason that we're able to maintain Knight's Law, and the reason that we expect that we're going to be able to maintain Knight's Law for many years to come, is because we're constantly evolving the technology and the tools and the operations of our foundry. We bring in new technologies that allow us to reduce variable costs. We bring in new processes that are more efficient, that save steps, that can operate at higher throughput. One particular example of that I want to highlight is advances in being able to combine many prototypes together in a single well or a single tube. So instead of needing to dedicate one tube per prototype, in which scenario our scale is limited by how many tubes we can push through the foundry every day, by combining many prototypes inside a single tube, and we can, in some cases, combine hundreds of thousands or millions of individual prototypes in a single tube, that really unlocks incredible new levels of scale and throughput through our foundry. We call that one multiplexing. That's just one of the kinds of technologies that we're on an ongoing basis introducing into our foundry. And so what that means is what we've been showing you today is the Ginkgo Foundry of 2021. We really look forward to seeing you again soon, when we'll be able to show you some of the new technologies and operations that we're bringing into our foundry and are helping to drive our ability to program cells.
So I've been really fortunate to be part of the Ginkgo journey for nearly 5 years. And in that time, I've seen one foundry go to now just recently opening the 5th foundry in the company at a scale that just, quite frankly, blows my mind. What the team's really been able to do is take all of the best of the life science technologies that are out there today and put them together in such a way to create an unprecedented scale. And you can see it as you walk through the different foundries, from the 1st foundry to now the most recent highly automated 5th foundry. And when I sit and walk around the foundry and talk to people, I just get blown away every time, because I think about the implications of what this could be and how this can change all different kinds of markets and create all kinds of different opportunities for people everywhere.